Okay, hello everybody. Give me just a second here and pull everything up. All right. And okay. So today, can everybody see my screen? Okay. All right. So what we're doing here today is we're going to talk about decoding the mystery of Kjeldahl. Kjeldahl basically comes down to one fundamental thing, and that's really understanding the stages. Once you understand the stages, you can make decisions as to what's going on with your system, really know what's happening here and there, make sure you get quality results at the end. So with that in mind, let's go ahead and begin to discuss what we're talking about. All right, so before we begin though, with the chemistry, I wanted to go over just a couple of things. First of all, this is the first in a series of the webinars based on decoding the mystery. The first of which is today, what we're talking about is the chemistry, and make sure that we understand the processes themselves and that it's really not complicated, but it is a process and it has specific steps. And then the next webinar coming up in January is going to be about user maintenance and then do it yourself. Okay, there's a certain part of the manual, usually chapter 6 or chapter 7 within the operation manual, where you can find all the maintenance information that you need for users to be able to tend to their instruments to keep it running at peak performance in between PMs. And then we also have a do-it-yourself kit for those who want to take that on and tend to their systems at a little bit of a deeper level. All right, and that's going to be presented by Steve Graham. He's our service engineer out of the Austin, Texas area. That actually might be broken up into 2 sessions depending on the length. And ultimately, at the end of the day, when it comes to the user maintenance, what we're going to do is try to make it a little easier for everybody, because what we're going to do is chop it up into segments. So if you, let's say you have a question or an issue with your sample tube system, your sample side, okay, fine, you don't have to search through a 45-minute webinar. It'll be directed toward that, and the same thing true with aspiration, titration, whatever the case may be. Okay, that way hopefully what it'll do is help you to fine-tune, get some instruction, and be able to follow along to keep your systems running healthy. And then later in 2018, dates are not formal on that yet, those are just projected for right now. What we're looking at is we're looking at application review notes to be handled by either our in-house or field application support people, both of which will go through the application note, discuss the chemistry, and discuss the system itself to make sure that what we're doing is we're following the protocols as they're set forth. Okay, so without further ado, let's go ahead and move on into our system. And the one thing that we look at when we first get an instrument is we have this wonderful little thing. It comes out, everybody's happy, it's shiny, they want to see it, they want to take it out and play with it. All right, so you unbox your system, it's installed, you're learning how to use it, everything's going well, and then all of a sudden you see the first signs of trouble. You make a quick phone call, everything looks good, get it back to going where you want it to be, but maybe we don't uncover the bigger problems, and before you know it, this is what you end up with. Okay, just on a little side note, for Kjeldahl, all technical support by phone and by email is free of charge. So by all means, if you have an issue or a question, give us a call. Don't let it get to this stage, because the one thing that we want to do is understand that gremlins really don't exist. They are created, okay? And commonly they're created from a lack of understanding. And sure, there are mechanical failures and there are electronic failures, no doubt about it, but for the most part, gremlins don't exist in our instrumentation. It's just a matter of our understanding and how we address it and how we maintain things at peak performance. All right, so to really get us going, what we're going to do is we're going to go through a brief history and a description of the chemistry. By doing that, we're going to understand that this has been around a long time, and we'll be able to really work with the same fundamentals that we saw for many, many years. We'll learn a little bit about why we digest samples, the importance of consistency. One of the things that I really want to cover is a lot of times old methodologies say you have to distill and then bring to a certain volume. We don't really have to do that anymore. The primary reason is because of the strength and the consistency of the steam generator. But we'll cover that here in a little bit. And then we'll go ahead and talk about the Buki product lines just a little bit to kind of give you an idea of what what we do have to offer, and we can meet people where they are based on their chemistry and their needs. And then finally, we'll open the floor for a general discussion. All right, so moving on, when we talk about the chemistry itself is well over 100, approaching 150 years old. And ironically enough, these are still the same basic processes: digestion, distillation, and then collection at this point. Titration came a little bit later, and we'll talk about that here in a little bit, as well as being separate. Okay, so when we talk about digestion, that's going to be our first point. Principally what you have is you're going to have a concentrated acid with some salts that help to hold the sample, the nitrogen in place, while we transfer it and get ready for the distillation portion, which is through here. All right, so hang on just a second. Okay, so now in moving forward, there we go. All right, so through the years, we see originally that we had the copper and potassium salts. It was all good, everything was looking good, but people wanted things to go faster. So mercury and selenium came about. The only problem is we had certain toxicities that came with that, but they did increase the rate and the speed by which we could digest. The next chemical that we see there is titanium, and again, the same kind of thing in combination with the copper and potassium salts that can increase the rate of reaction. Sulfuric acid is the most common digestant. Some people use a combination blend, but for our discussions today, we're going to talk about using a complete digestion utilizing a concentrated sulfuric acid. Sodium hydroxide is commonly used for the alkylation of the sample once we get to the the distillation stage. And boric acid is what we're going to hold the nitrogen with in a complex, and then back titrate, and commonly using an indicator. Most of the time we're either back titrating with hydrochloric acid or a sulfuric acid with a known concentration. Okay, so again, just a little brief comments on mercury and selenium. Very good, very short digestion times, even for things that had high hydrocarbon content like a fatty acid or a fatty sample, but realistically, we can't use them. Why? Toxicity, environmental regulations prohibit us from using those anymore. A little bit slower than the mercury digestions is titanium, but on the other hand, actually has very good recoveries. Copper and potassium are still the most common, and coupled with titanium is also a very good digestion. All right, so when we talk about digestion, what are we actually doing? First of all, it doesn't matter whether it's a solid or a liquid. What we're going to do is liberate whatever it is from the matrix that's being held. Most commonly, your inorganic and organic held nitrogen. The inorganic basically is a simple dissociation and goes into solution right away, but the organic does require being digested, in other words, liberated from the hydrocarbon matrix. Okay, so to do that, what we do is we're going to use heat, sulfuric acid, and the catalyst. Between those things, what we do is we'll take the temperature up to about 420 degrees for about 90 minutes, but mainly what we're looking for is that nice little blue-green color that you see, and that gives us the ammonium sulfate. And any kind of black or brown that you see is incomplete digestion. So we want to make sure we're going to get us to that color. And now our nitrogen will be fixed as an ammonium sulfate. Okay, a couple little details here. When it comes to the digestion, this seems to be the biggest complication for people who have losses or experience low recoveries. The biggest issue is incomplete digestion. So what we want to do is want to make sure that we set up the temperature zones and the various zones that you see here. So that way what we have is we have the complete zones set up, so that way we can complete the digestions. All right, so first things first, what we have is we have the boiling area. This is where your sample will be. This is where your temperature is going to be the hottest. Sulfuric acid and catalyst will be housed. Next, what we have is we have the condensation zone. That condensation zone is set up to basically wash and reflux to make sure that anything that goes up and above is being washed back down into the sulfuric acid and continues with the digestion. Now, very important is that safety zone. We want to make sure that what we do is we don't get any sample up within that safety zone. And the best way to do that is to utilize a little bit of the sweeping, if you will, helps to kind of cool that chamber, so that way the condensation zone sets up, and we do get a good reflux that way. All right, so a couple little things about the engineering design here is the thickness of the glass, and then also this taper and connection joint. Okay, the thickness of the glass is very helpful because it adds to the length of the life of the sample. The sample tube, and so it keeps you using the same vessels again and again for a much longer period of time. And then the taper itself helps to also set up that zone, so that way we don't have issues along that line. And then it also helps to develop that seal. Based on that seal, the one thing we want to do is make sure that what we have is we have a good snug fit, so any fumes are being swept away rather than being released to the atmosphere. All right, so moving on. Again, what we want to do, and we're going to look at a couple different models for Buki. What we have is we have the blue-green to clear. That indicates the end of the digestion. So what we're looking at here are two different versions, two different styles of getting to the same point. The first of which on the left is a block digestion system, where the glass comes in direct contact with the block, the heating block, so therefore you have a direct transfer of the heat from the block to the glass to the sample. On the other side, what we have here to the right is going to be the infrared type of digester. And so it's more of an indirect. So what you have is you have heating to the side, and then from there what you have is you have a higher temperature that you're going to be working with because it is indirect. In other words, we have to get the heat from an area where the heater is not in direct contact with the glass. There's a space, and then you have the glass, and then you have the sample. Okay, so when we look at the two different together, we do accomplish the same things, but we do, if you notice, see temperature differences. So those temperature differences right here with the block digester and here with the infrared digester. Nothing major, just a simple difference is all it really is in style of how we want to digest. Okay, so step two, moving on, so step two is distillation. When we look at the distillation, the process is pretty straightforward. We're going to add some water to control the rate of reaction. Do keep in mind that what we're working with right here is we have a concentrated sulfuric acid. One of the things that I needed to mention just a bit ago is when we do the digestion, we're going to have a 2-to-1 ratio of the catalyst to the sulfuric acid. And the whole premise of that is making sure that we don't have a crystallization. Okay, so we want excess sulfuric acid after the end of the digestion, or at the end of the digestion. Okay, so we don't want to hit a strong acid with a strong base because we're going to have a very violent reaction. So the first thing we do is add water. The next thing we do is we're going to add 32% sodium hydroxide. That volume can be a little bit higher, a little bit lower, but it's roughly speaking usually around 50 milliliters. Okay, some people work with different concentrations. Most commonly, you're going to see a 40 and a 50%. Based on methods of old, but we do really recommend 32%. It helps to preserve the length of the life of the glass, and it will help to control the rate of reaction as well a lot better than a 40% would. Okay, and the whole idea is to generate the nitrogen and alkalize it to generate the ammonium gas. Once you have the gaseous ammonia, what we'll do is we'll recondense that and then capture it and complex it in a boric acid solution. All right, So this is one of the primary things that I like to talk about here. We talked about the quality of the glass, and here mentioned it just a little bit ago, that the consistency of the volume. And the reason for that is that we don't have to go to a final, bring the sample to a final volume post-distillation anymore, is because of the quality of the steam generator. When the steam generator is run at 100%, it's very easy to match and map the volumes that you get. They're very consistent in delivery of the same volume time after time after time. So therefore, when we're working with our blank correction, the one thing we can easily do is we can say, okay, it's going to distill this amount of volume every time. So therefore, we can account for it with a blank correction value. We'll come to that when we talk about that in the calculation. So in the meantime, what we're looking at here is this is taking the place now of this. So the steam generator for Buki is one of those big differences that I think makes all the difference in the world. Why? Because at the end of the day, only two things come over in the distillation from a digested sample. Only two and only two. And that is water and ammonia, and that's it. So the consistency of that distillation is extremely important, and that's what we are able to accomplish now with our steam generators. And by the way, it doesn't matter which model version for Buki that you have, the steam generator is the same in every single model. Okay, so in the distillation details, one of the things that we also want to cover is making sure that we have this neck, and the shape of the glass does come into play. So again, what we have when we're looking at this is we're looking specifically at this range as you see here. If you notice that we have a little black adapter, just basically a rubber, what we call a bung, and so the taper in the glass helps to build and develop a better seal. The one thing we want to do is make sure that any ammonia that's generated goes through the condenser and thus collected. Okay, so again, the shape of the glass, quality of the steam generator, both make a good, solid distillation possible for people to get good results, similar results, time and time again. Okay. All right, so I commonly see in old methods 40 and 50% sodium hydroxide being added. Simply put, if you look at the graph, and by the way, this is just a pH probe reading as we're looking at it based on a potentiometric probe, the one thing that you see is here at 32%, we are controlling the rate of reaction, easy to match, easy to work with, and easy to develop a start point if you're planning on running a start point titration. If you're using 40% or 50%, your start point is not as well defined. And so therefore you can have a randomness in the reporting and the results. So between the combination of the 32% sodium hydroxide and the water that we add for dilution, it makes sense that what we do is we utilize, and we can see pictorially now that 32% is the proper solution concentration to work with. Okay, to add a little bit more to that, what I want to bring to your point on this next slide is, if you look, and I really should have blown this up, but basically that is a variable point. Even though it's a minor difference, it can add to a big difference when you're talking about Kjeldahl in the world of protein, because many times their recoveries need to be between 99 and 102%. With that being such a tight window, even small differences can make a big difference. So these are two back-to-back runs using 40% sodium hydroxide, and you can see there's just that slight variability of what it calls a start point. Okay, and that will have an effect on your results. Long story short, 32% is the way to go. Okay, so now we'll look at a little bit of the distillation parameters, and you'll see that basically they're pretty much the same. What we're looking at, whether it be food and feed, or whether it be dairy, or whether it be wastewater, whatever, it really doesn't matter. The primary thing is the consistency. You see the dilution, you see the sodium hydroxide, you'll see a reaction step, which is typically between 1 and 5 seconds, sometimes a little longer, sometimes Well, not really any less than 1 second. But then your distillation time is always fixed. Commonly, what you'll see in a distillation time is between about 3 minutes and about 6 minutes. And that's basically what we're seeing here. You have 3 minutes being 180 seconds on the right, and then on the left you see 300 seconds, which is 5 minutes. Steam power for nitrogen determinations is always set to 100%. And then the rest of it we'll talk about here in a little bit, because that really goes to titration. The only one that really kind of sticks around here as far as this is concerned is a stirrer speed. But again, we'll talk about that here in just a little bit, and the differences to why we have two different speeds. All right, so moving on. Oh, where am I at? Okay, so now basically just to cover the distillation again, what we're looking at is control the rate of reaction. Yeah, okay, control the rate of reaction, generate ammonia, and then condense and hold as a borate complex, ammonium borate complex. Another important facet is going to be the condensation water for the ammonia. Okay, so the condensation temperature that we need is roughly speaking around 20 degrees C. So most commonly people will use one of two methods. One is tap water and the other is a chiller. Okay, there's advantages to both, and there's clear disadvantages to both as well. With the chiller, obviously, it's an additional cost, where water through a tap is cheap. But you do have other considerations to take into account. The first of which is where you live in the United States. Commonly, what I see is somebody in the state of, like, let's say Louisiana, is going to have a chiller, whereas somebody in Wisconsin will not. They can use the tap water for the condensation of ammonia in the water. And the reason being is because that 20 degrees is roughly the break point of where we're going to start seeing ammonia losses. In Wisconsin, typically your tap water temperature is going to be about 18 to 19 degrees C, whereas in Louisiana you can be as high as 21 to 22 degrees C, and you will have losses. Okay, so tap water, a lot of people also can't really allow water to just run down the drain. So if you work in California, you are looking at a chiller. Okay, but the ideal is to have the water temperature for the condensation between 18 19 degrees C, and it's a very good system to run. You can go as high or as low as 16 and still have very good return without having problems going the other way where we're condensing too early. So advantages, a little bit of optimization will go a long way toward making sure that we get all of the ammonia to come over, and it's very easy and simple and easy to understand. Okay, so now we come to the titration. The titration is very simply we're taking the boric acid complex that's holding the ammonia, and we're putting, that's being held now in a 2 or 4% boric acid solution, and what we're doing is we're back titrating to a start point. Usually it's set to 4.65. Now what we do commonly is we have two different types. One is a start point titration and an end point titration. The start point titration, if you think about it here, just quickly going backwards, in this graph, a start point titration would basically pick a point right after the beginning of the titration itself. And in this case, it looks like about 4.5, it's a little bit more than that. And it's literally going to titrate directly back to that same point and call that the amount of in milliliters that are used. And that does not require standardization of the boric acid. On the other hand, an endpoint titration specifically is going to get us directly to an endpoint based on the pH of a 4.65 or whatever number that you determine. Okay, so, but it's commonly used, most commonly the endpoint is going to be 4.65. Now, when we're talking about colorimetric though, we do have to standardize to 4.65. Commonly we have two different indicators that are used, and one is a share indicator, and then the other is a mixed indicator that includes bromocresol green and a methyl red. So when you standardize your acid, you're going to take your boric acid, whether it be 2 or 4%, add your indicator, and then use a very low concentration sodium hydroxide to get us to the exactness of a 4.65. And the colorimetric sensor does need that as well. So whether it be potentiometric and you're looking to use color as a secondary source of making sure you're at the right endpoint, or whether you're using colorimetric to do the determination itself based on the wavelength, either of these indicators and standardization to 4.65 is very important. Okay, so just a quick example of what it looks like. This is a potentiometric probe, and you see a colorimetric probe on the right, both of which basically are going to the same thing, and we're looking at the shear indicator. So, and both of those are standardized to 4.65. All right, so now when we're putting it all together, what we're looking at is we're looking at a digestion and then plus that of a distillation titration. Very straightforward, very simple, and we now have all of our 3 steps in play. So when we're looking at this now, we're looking at, and I'm just going to kind of review the left, and then we'll go ahead and draw the parallels to the right. So you see the basic parameters of the digestion on top. On the left, we're using an infrared heating system, so it's indirect, so the temperature's up to around 510. And then we go to the distillation system. It looks like we have the dilution, the sodium hydroxide, the distillation time is 5 minutes, and then we'll talk now about the stirrer speed. So the stir speed that we're looking at right now is we start off with a setting around a mid-range somewhere around 5. Okay, the primary reason for that is, if you think about it, the one thing we don't want to do is splash. So we have a low volume because we only have boric acid to begin with, and we've dispensed only what, probably like 50 mils. So now we want to keep that stir speed kind of just moving so that we have a good mix and good surface contact when the distillation is taking place. And then when we're ready to titrate, what we're going to do is increase that rate so that way we can be closer and have a better mixing to get us to a finer end point. Okay, hopefully that makes sense, very straightforward in that regard, but that's the reason for the 2 stir speeds. Okay, and then drawing a parallel to the right, here you have a block digester, so our temperature is only to 420. We are using a colorimetric sensor, so our stir speed is actually higher. And the reason being is, if you remember looking at this here, I don't know if you can see it, but basically what we have is we have a fine wire mesh that you have to look at right in there. Very, very tightly you can see the wire mesh. And so with that wire mesh needing the sample needing to, the liquid being where you have to mix it very well, the one thing we want to do is go through that wire mesh very quickly and easily, and the way to do that is to increase that speed. Okay. All right. So moving on, the next thing that we have is that we have the calculation. So again, we talked about the consistency of the steam generator. So we can, since that is a very reliable volume that's distilled, what we can do is we can determine a blank and then take that blank out. And so you can see there's a sample. We subtract out the blank in milliliters, and we're talking about the titrated milliliters now. So let's say you have a blank that's been titrated about 0.5 milliliters of the titrant acid, and then your sample is somewhere around 4.5 milliliters. So basically it's going to be a 4.0. 4.0 minus a 4.5 minus a 0.5. Anything along that line. The main thing is we're accounting for that blank. You take into account the sample size, whether it be solid or liquid, and the math calculation is pretty straightforward from there. N being the normality of the acid. When we're talking about percents of protein or protein itself, what we also have to take into account is the addition of a protein factor. Okay, so the protein factors are something that have been around for a long time. They're accepted conventions, and the calculations were done. The oldest I've seen is from like the 1930s or 40s, somewhere around there. And in fact, the sheet that I have, it's very aged. Let me tell you, it's really kind of funny. But But the main thing is when you're dealing with a different type of a sample, whether it be a meat, whether it be a nut, whether it be a milk, each one has different types of amino acids. So we account for them separately and differently. Like, for instance, what we see here is milk. The protein factor is 6.38. For a nut, it's 5.4, and it varies in between. And if you have an unknown, commonly what people will use is a 6.25 protein factor. Okay, so we take that into account, and again, that gives us the percent protein. And so basically what we're looking at is we're looking at the same exact process, whether it be water, wastewater, or whatever else, along with anything that's food, feed, biological. We may handle the digestion a little bit differently, but the distillation is commonly very similar one to another, and we just take into account the differences in the math. Okay. All right, so a little bit about Buki's product lines. Commonly, when I'm talking with people, the first thing I'm going to talk about is your throughput. And I'm going to start based on our conversations about the distillation systems and then build around it. So first things first, we're going to say, how many samples do you run? Very simple question. You give me an idea of where you're going with that. And the next question I'm going to ask you is, what kind of features are you interested in? Now, budget does come into play for people, so I don't want to, skirt that. But realistically, the more features, the more automation you can get, it's actually a lot easier. The more manual, it's more labor intensive, which pretty much that's the definition of manual. So when we're talking about these instruments, the one thing that we want to do is we can meet you where you're at. If you have a limited budget, all right, fine. We can work with you to figure out what you need from that point to give you the best bang for your buck, so to speak. If you have something where you're running, 50, 80, 120 samples a day, we can accommodate that as well. We just need to talk about how the degrees and levels of automation and make sure that we have the right match to your need. In other words, provide the solution. And then once we do that, we'll go on and talk about the ancillary products that go along with it. Most everybody needs a digestion of some sort. The 20 milliliter, the 20 position rack, the block digester you see on the right, that rack will slide directly into the auto sampler. And on the left, the other two, they give you a lot more flexibility. But again, there's no auto sampler. You have to manually move samples around. Okay, but the one thing that you do gain is you can gain the variety of the vessel sizes. So the sample tubes can either be 100, 150, 300, or 500. It does not really matter for those models. However, the block, and the reason being is because it's an indirect heat, we just change an insulation block. On the other hand, when we're talking about the 20 position distillation unit, we have to be very specific because that is a direct contact of the block to the glass. Okay, so it is a bit of a limiting factor in that regard versus the more versatility that you see with the infrared, but which one better suits your needs is the question that you need to ask yourself. To go along with that, we kind of talked about this a little bit with the different chemistries, but basically what we have here is we have the different Caltabs that are available as well. These are very commonly used. And what you see is that the Missouri tablets, which is probably the most common, has a composition of potassium and copper salts. And then when you're talking about titanium, you have the same copper and potassium salts with the addition of a titanium salt as well. And then an eco is basically just a little bit less cost. It all gets you to the same endpoint, ideally. The one thing I want to point out to you is take a look over here and here. We talked about our ratio of 2:1 of the sulfuric acid, and that is a concentrated sulfuric acid to the gram weight of the tablet. So we want to start off at least a 2:1 ratio. And I say at least 2:1 because there are times where fatty acids and other things, other hydrocarbons, can come into play. And we need to make sure that we account for that so we don't overconsume the sulfuric acid and then crystallize. There's a nice study that came out of Canada that talks about that specifically, where you can do the math to determine if you need more than the 10 milliliter minimum that we recommend. Okay, if anybody needs that, by all means get in touch with me and I'll get you the study. All right, so the next thing we talk about is a scrubber. When it comes to the scrubber, basically what I'm going to recommend every time when it comes to Kjeldahl is a triple scrub, whether it be the triple scrub or the triple scrub eco. Even if you're dealing with solid samples, you will have some moisture. You don't want it to go into your neutralization vessel, which is a volume of a blend of water and sodium hydroxide, typically an 8 to 10% blend. And so what we want to do is we want to make sure that the first thing we do is condense that. So step number 1 is condensation, and then the neutralization using that sodium hydroxide, and then an absorption just in case we have anything else, and that all protects the pump, that draws the vacuum, that draws the fumes away from the digestion. Okay, the difference between the eco unit and the non-eco unit is the eco unit basically has a valve where if you're plumbing a tap water to it, it has a shut-off valve. So when you have the unit itself plugged in and you have the tap water on, when it's not in operation, that valve is in a closed state. So you're not wasting and having water just run down and out. And then also, it includes an electronic control where what you do is you have a power cable connection. And so it can actually share the same power with the digestion unit as long as they're the same voltage. Okay, so the matching voltage is very important there. If you're running at 220 for the digestion unit, then you're running at 220 for the scrubber. Conversely, if you're running at 110, you're running at 110 as well, but you don't want to mix and match if you want to connect the two. All right, and then for those who need it, you have the chillers. What we have, and if you look at the bottom of the page, we have the Kjeldahl, and if you just have a standalone system or a standalone unit, distillation unit, then the 308 is what we recommend. If you're going to be digesting and distilling it at the same time, in other words, you're running quite a few samples, you're going to be running everything, and it's constantly going to be going, you'll want to have something with a little bit more wattage, a little bit more cooling capacity, if you will. Okay, and wattage is key to get us to that cooling capacity. All right, so as we put it all together, what we're basically looking at here is we're looking at 3 steps. Step 1, digestion. Step 2, distillation. Step 3, titration. So it's not really that complicated. The primary thing, though, that you have to understand is that it is a process, and we do need to optimize that process. The funny thing is every time I say that, well, it should be the same every time, it turns out that it's not that way at all. Everybody has a little bit of idiosyncratic thing that goes on, and so we work to optimize that. For the most part, we have some pretty good guidelines with our application notes, but again, realistically, what we do is we want to optimize so that way we have a consistent singular method, maybe a couple of different methods if you're doing different processes or what have you. But we want to keep it as simple as we can at the end using the instrumentation. So we're going to optimize that process as best as we can. All right, and then lastly, we do have some resources that are out there in literature and then application notes. The Kjeldahl knowledge base is fairly extensive, and so what you have there is you have an ebook. You go up, you register, and you have access now to the Kjeldahl knowledge base ebook, and it has quite a bit of information, a whole lot of information about Kjeldahl. Gives you a little bit of company history and background, and it talks about a lot of methodologies and regulations and things along that line too, not just chemistry. However, the practice guide is pretty much focused on just the chemistry. So it gives you the pointers based on your gram weights of your samples, the expected amount of nitrogen, what the concentration is of the titrant should be, you know, those kinds of things that really assist you to make sure that you have an optimized system for your samples. And then in the application finder, again, it's a registration, then these come up for you, and you can literally just fine-tune your search based on your product as well as that of the industry that you work in. Okay, and that'll give you the guidelines. But again, the one thing I do recommend is Buki does not charge for consultation. So you give us a call, you send me an email, and we will talk about it to get you the right fit. All right, so the big question is why? Why is nitrogen so important? Well, because it's used in industry, it's because it's used in public health, and because it's used to drink. Okay, we use water to drink on a regular basis, and I for one like to drink clean water, not infected with things that could make me sick. Okay, protein deficiency, one of the things that we've seen and looked at historically. I could have pulled out some graphic pictures that show protein deficiency, but I think this is better. What we want to do is we want to make sure that when people are getting what they say they're getting to help them with their health concerns, that the protein numbers are right. Again, those with health concerns going the other way, those who are working on specific and strict diets, those who are just simply watching what they take. Protein is a very important aspect. You see it in athletes on a regular basis. And then on the bottom left-hand side, we see the importance based on a fertilizer. When you have a fertilizer, nitrogen is actually an extremely important part of for farmers to make the decisions based on what they're growing. Okay, so to kind of begin to wrap us up, this is our first in a series of webinars again, the first of which we basically covered extensively a lot of the chemistry and in decoding, in an effort to decode any mysteries that are out there. The first step is an understanding of what we're doing. The next in our series is going to be the user maintenance and the do-it-yourself kits, and so therefore we're going to optimize systems from a physical standpoint and make sure that we're getting good chemistry time and again and again. Okay, and then lastly, we'll go through some application note reviews where we're literally looking at application notes for the variety of people, for the variety of industries that are out there. January is set. Our speaker is Steve Graham. I'll have a specific date and people will get the invitation, and but it will be the middle to the end of January. As far as the applications are concerned, they're not set in stone yet. If there's a greater demand, I may have them earlier. It's just a matter of having enough time to prepare and not trying to hit too many people with one thing, with something all at the same time. And then again, what we're going to do when it comes to the user maintenance is we're going to chop the webinar up into small pieces. So that way, if you have an issue with an aspirator, you have a question about how this works or how that works, you don't have to go through a 45-minute to an hour webinar. You can go to a 5-minute segment or a 10-minute segment, whatever it takes to cover that aspect that you're interested in. Okay, so understanding and balance, that's really the key to success. An understanding of the chemistry and understanding that that chemistry has a balance, whether it be physically related or whether it be based on your sample types, and optimizing your system to fit that. Okay, a couple of websites for you to be able to address, and a toll-free number for you to call with your questions and what have you. All right, so now I think I'd like to go ahead and open the floor and tend to some questions, and some have come in already, so I'll go ahead and go back to address them. Okay, first of which is, what's the maintenance I can do on my own? Okay, basically go to your manual is what I'm going to tell you. We have in chapter 6 or 7, depending on your operation manual and what model you bought, there's a list of what to do weekly, daily, weekly, monthly, semi-annual, and then annually. And then, of course, we have our PMs. So, but if you have any questions more fine-tuned, by all means, give me a call. One of the things I do recommend is that isn't quite as spelled out as well as what I'd like, and that's in discussion with your sodium hydroxide pump. The biggest complication that I see people run into is my sodium hydroxide pump is dispensing less. And what that tells me is that we're seeing some crystallization within that pump. The easiest thing to do is flush it anytime you're going to have it dormant. Okay, it's one thing if you're running overnight or running one day, it's going to sit overnight and then you're going to run again the following day. That's not that important to flush. But let's say you're going to run samples on Tuesday and you're not going to run samples again until the next Tuesday. At the end of that Tuesday, the one thing that happens is that sitting there in that strong base solution within that valve, within that pump, is you can see some crystallization. So we want to minimize that, and the best way to do it is to do a water flush. It takes just a couple of minutes to do, and then at the end of when you're ready to start up again, you move it back over to the sodium hydroxide, and while you're doing your warm-up and priming, you're already rerunning the sodium hydroxide back through, so it's ready to roll as soon as you're ready again. Okay, so how do I talk to someone? Probably came in as a fairly early question. Basically, if you look at what I have on the screen right now, that'll get you to us within our technical support. And the call will come either to one of the field application or in-house application support, and or it may end up coming to me as well. All right. And that toll-free number that you see, 1-877-692-8244. And if you go to the website, you can also ask a question. It'll go to a general mailbox, and from that general mailbox, it'll be distributed. All right, the next question. Okay, the next question is asking about what we do again here based on the distillation main page. Okay. All right, so when we talk with you, and this is kind of reiteration of what we talked about just a bit ago, and this question came in probably early as well, but when we talk to customers about the best fit for their lab for the solution that they need, is we talk to them first about throughput, and then we follow that up with the degrees of automation and what will work within their budgets, and then we build around it. Plain and simple. Features seems to be one of those things that gets a little bit overlooked, and so that's one of the things that you really kind of need to take a look at and see what's the best fit for you within, and help you determine that, yes, this is what we want, this is what we need, I can defend it to purchasing and get what it is that I'm after. Okay, and sometimes it's a little bit lower in budget. That's fine, no big deal. We have a solution for you no matter what. Okay, the whole goal is the right fit for you. Doesn't matter to me which one you're looking at. What really matters to me is that you get what you're after, so that way everything is a win-win. All right, moving on to the next question. How many samples can you distill at one time? Okay, bit of an interesting question. Basically, when you're talking about distillation, it is always a one-by-one. Okay, now whether or not you have an auto sampler may be the question you were asking. When it comes to our auto sampler system, the K375 coupled with the K376 and or K377, you have the 20 position, and with the K377 you have a second 20 position system. Okay, so the answer to that would be 20. There is an emergency rack on each one of those, where if you have like QC samples or you have an emergency set that you need to run, you can actually insert it within the line itself, and that's an additional 4 positions. So basically you have a 24 position system. All right, so you can run that automatically, and if you have the K377 as well, as the K376 is running, you can load the 377. As you're running the 377, you can go back to the 376 and load it. So you can literally and virtually be continuous if you want to go that route as well. So I don't know if that answered your question or not, but as far as actually distilling, it's always one sample after another, whether it's manually putting on a tube or whether you're utilizing an auto sampler. Okay, I hope that answered your question. Okay. Audio cut out during the explanation of the glass. Okay, so just real quick to go back to the quality of the glass, let me go to here and bring a picture back up. All right, so the engineering design of the glass is very straightforward. The thickness of the glass that Buki provides is 2.3 millimeters, whereas most other people who make Kjeldahl glassware, the thickness of the glass is 1.8 millimeters. So the thickness of the glass does add to the length of life significantly, and also adds to the strength. So the one thing you don't want to do is have anything that's going to compromise, and you're going to have a spill of a concentrated sulfuric acid, and or it can't handle the heat and then the alkylation step. So you do have to inspect the glass on occasion, but for the most part, unless you're a bull in a china shop and you're dropping the glass, they should last you a very long time. And then, of course, is the taper design. The taper at the top, that flare, that kind of pinches, and then you have the flare at the top for the connection, very specifically to increase the security of the connection between the sample tube and that of the distillation unit to make sure that all of the ammonia is going forward to the condenser so it's captured. Okay, I hope that answers your question on that. The quality of the glass is actually very important. The next question is a difference between Kjeldahl and Duma. Okay, we really didn't cover Duma here, but basically let me just say this. What we have with Duma and what we have with Kjeldahl is, to me, I don't care which direction you go. Buki offers both solutions. The primary thing is which is the best fit. If you're in the USP world and you're needing to report to and or follow USP protocols, USP does not recognize Duma as a protocol that you can follow and report. So Kjeldahl would be the choice if you're following USP. If you're dealing with something else like environmental, the biggest limiting factor to Duma is this, and that is sample size. You're limited to sample size of up to 1 milliliter of sample and or about half a gram or so of a solid. Maybe a little bit more, commonly a little bit less. So if you have something that has a low nitrogen concentration, like a wastewater effluent or something, or a drinking water or something like that, you'd never be able to get the volume high enough to put onto a Duma system. On the other hand, let's say you're a nutraceutical company and you're making a protein powder, if you will. Duma is a perfect fit for that type of application, or some kind of an oil, or some kind of a yogurt, or something that's got a much higher quantity of nitrogen and commonly packaged in a protein of some sort. Then Duma actually is a very, very good system. It's very short, it's combustion technique, it does not require digestion, the sample prep is only but a couple of minutes, and it's a very consistent process. The only complication, again, or the biggest issue, is sample size. So if you want to call me, we'll talk offline, and we'll make sure that we're going down the right road for your best fit. All right, so moving on. Okay, I found that combustion analyzers require a lot more maintenance than Kjeldahl. Well, I don't want to really discuss other vendors, but basically our systems are fairly simple. Other vendors require a breakdown to build it back up. Ours has a slide-out furnace, and I can discuss that, but again, this is not a Duma conversation. By all means, let's talk more about this offline. And I've got your email address here, so we will discuss that. Okay, I'll get a hold of you and we will discuss it. All right, is there any benefit to 25% sodium hydroxide for fatty food samples? We currently use the standard methods for all our sample matrices. Should there be different methods for high fat, high salt, and food samples, etc.? Basically, when I talk about optimization, the one thing I try to do with people is we have one, maybe two methods at the most, if you have a consistent type of a sample type. To me, the primary thing is simplicity. We can optimize a system. If it's a little bit of overkill, it's not a big deal. Why? Because if we have an excess of sulfuric acid or we add an excess of sodium hydroxide, we want to make sure we add enough sodium hydroxide to fully alkalize, but any way you look at it, doesn't really matter. Why? Because it doesn't distill. Only two things distill at the final end process, and that is going to be the ammonia and the water. Okay, so if it doesn't distill, we can add as much as we need to make sure that we get all of the digestion completed, and then add as much of the sodium hydroxide that we need to completely alkalize. The whole thing is to try to build an optimized method that can handle all of your sample types. That would be my goal in our discussions. Okay, so what is the maximum sample volumes that can be processed in the K355 and a 446? All right, so to do that, let me go ahead and go back over here. When we look at the K446, the K446 is one of our 20 position systems. Okay, so that's your limit there is 20. However, the K355, what you see here is a manual unit. Now the distillation commonly is between 3 to 5, maybe 6 minutes. Most commonly somewhere between 3 and 5. But the maximum number of samples, maximum sample volumes, Okay, so with the 446, if you're talking about, like, let's say a liquid volume, or you're actually meaning throughput, if you're looking at volume, basically you're relegated to that of the 300 milliliter tube. So roughly speaking, about 200 milliliters is going to be the maximum volume you can run per sample. Now, when it comes to throughput, and just so we're clear, I don't really know which direction we're going, so I'm just going to explain both. When we're talking about throughput, your real limiting factor is about the time it takes to digest 20 samples is going to be about the same time that it takes to distill those 20 samples. So if you're running a rack of 20 and you're running the distillation unit, basically speaking, the digestion should be able to keep up with the distillation depending on how quickly you sample prep and how quickly it goes back on. The common digestion time is 90 minutes plus about a 20 to 30 minute cool down for the block digester. It can be a little bit faster if you're using the 6 or the 12 position because of the infrared heating, but realistically you're looking at about 2 hours on a regular basis for the digestion. And for those same 20 samples at 3 minutes apiece, you're again looking at about that same time frame of about that an hour, maybe 2, to complete the distillation / titration. Okay. So the next question, I hope that answered your question, by the way. I covered both angles of what that could have been. Hopefully it covered what you were asking. Okay, so how often should we replace the digestion vessels? All right, again, my recommendation there is inspect them. Realistically, the thickness of the glass, they should last you an awfully long time. But we're talking probably in the neighborhood of years, like 2, 2.5, 3, somewhere around there. And again, that depends on how many times you run. But ultimately, the things that you need to do is inspect them for either a star crack of some sort and or the wear and or etching on the glass based on the lip as it would connect to the bung. If you see an etching on the glass, that basically means you could be losing ammonia. So basically just simply inspect, but quite frankly, they should last you quite some time. Okay, and again, unless you're a bull in a china shop and you drop it on the ground, I can't help you because no one can. Anyway, all right. If my titration vessel does not turn brown, i.e. the boric acid doesn't turn brown following distillation. All right. So my first question is did you standardize your acid? If you did not standardize your acid, are you running a start point or an end point? If you're running an end point titration, you really do need to standardize to 4.65 because it's looking for that number that you assign it. Okay? If you're looking at a start point and you don't see it turn brown, shouldn't be a big issue. However, if you're dealing with anything colorimetric, we have to make sure that we standardize. So it sounds like to me, and I might be wrong, but you're adding the share indicator and you are not standardizing looking for an endpoint. I'm sorry, looking for beginning with a start point titration. It doesn't necessarily have to have the color change because the indicator is really not a part if you're dealing with a potentiometric sensor. On the other hand, there are people that I work with that they do standardize their acid to 4.65, their boric acid receiving solution, that is. And so therefore it starts off with a little bit of the brown color, and then anything that they do turns it to gray to a bluish color. That's going to, as you distill over the ammonia and or the additional water, and then that back titration is a secondary source of confirmation that you've reached the end point. Okay, so, but I'll contact you. We'll talk about that a little bit more offline and make sure that you're on the right track. There are a couple of questions I need to ask to get a clarification, find out exactly what's what. All right, so the next question is how is protein factor calculated for specific proteins? Okay, and going back to the conversation as we were talking about the calculation, those protein factors are conventions that have been around for a long time. Okay, so depending on they've been around since longer than I've been alive, and so they're still used today for things that were done, mathematics that was done, determinations that were done in the 1930s, 40s, or 50s, depending on what it was, and So those conventions is based on the protein source. If your protein source has the amino acids that make up milk, if your protein source is the amino acids that make up a meat, those have different values that have been assigned, that have been calculated, and so therefore we take them into account accordingly to convert the nitrogen from the primary calculation to that of protein. Okay, so simply put, it's a convention. All right, the next question, would we be able to email you with further questions even though no contract exists? The answer is yes in the world of Kjeldahl. Buki for Kjeldahl does not require you to have a service agreement and or some sort of a contract to talk with us and discuss things via email. Okay, plain and simple, you can get answers. All you have to do is reach out to us. But I've got your email. I'll reach out to you as well. All right. And okay, I see one last question here. How many samples can you digest at one time? All right, going back over to this slide. This slide basically gives us what we have. Basically, we have a 425, which is not pictured. That's a 6-position system. The 436 and 439 are both 12-position systems, and the K446, 449 is a 20-position. The difference between the 446 and the 449 is the 449 has an automatic lift and shut off. So therefore, you can literally set your last samples up for the day if you want to, press start and walk away, and when it's done, it'll lift the samples out and keep the lid down so that way it'll cool completely. On the other hand, if you're running a 446, it is a manual lift. Okay, and all the other models, by the way, are manual lift as well. Okay, so 20 is a maximum you can have in any of our digestion systems. Any other questions? All right. Well, I want to thank everybody for your time. Thank you for attendance. I do want to run just real quickly a reminder that what we have after we finish this webinar is this is a webinar that's the first in a series. We talk initially about the chemistry. We'll move on to the maintenance and the health of your system, and then we'll talk about some application reviews. And again, especially when we're talking about the user maintenance, that will be chopped up into little pieces, so that way it's easier for you to get what you're after to be able to do what you need to do. And we will have a video for those who want to do the do-it-yourself sort of thing. All right, just simply buy the kit. You'll have a link to a video that will help you to do the maintenance on your own. Typically the annual maintenance, it's not the full PM. Some people really want to maintain that level and be able to do things for themselves, so we want to assist you in that way as well. All right, so if there's no other questions, thank you for your attendance and your attention, and I look forward to working with you in the future. Have a good day.